Good morning, everyone. I am Bhavesh Devadiga, undergraduate student in Indian Institute of Space Science and Technology, Department of Aerospace Engineering. Today, I will be presenting my work, First Law Analysis of a Typical Domestic Pressure Cooker. This study develops a simplified thermodynamic model for a common household pressure cooker using first law thermodynamics to analyze its energy balance and performance. The presentation follows this structure. I'll begin with a brief introduction, then move to the literature review, methodology, results and discussions, and finally the conclusion. A pressure cooker is a closed vessel that traps steam. As the trapped steam increases pressure, it raises boiling point of the water. This allows faster cooking, reduced energy consumption, and often retains nutrients. The system is ideal to demonstrate the energy of the first law thermodynamics as heat enters and leaves through a mass flow of the system. A typical pressure cooker and its component can be seen in this image, including lid, gasket, pressure valve, and locking system, which play an important role in safe operation. The objective is to develop a simple thermodynamic model for the cooker and analyze its behavior using the first law. The study evaluates mass and energy balance, calculates the vented steam and change in internal energy, defines efficiency, and studies how parameters like time, volume, pressure, and temperature affect performance estimate. Several studies have investigated various aspects of a pressure cooker, such as energy efficiency, heat and mass transfer, energy management, fluid flow, thermal loss, pressure variation, and temperature evaluation. Flick simulated fluid flow and heat transfer in a pressure cooker using a three-dimensional computational fluid dynamics to predict gas and temperature evolution, including evaporation and condensation in the presence of non-condensable gases. Some phenomena that were difficult to characterize experimentally were observed in the simulation. Building on this, Rocca developed a model of heat and mass transfer that predicted the evolution of pressure and gas composition at different temperatures. The study emphasized that condensation was a major part of heat transfer to food and recommended reducing heating power once the desired pressure is reached, as steam escaping instead of condensing on food is a thermal loss. Ayub experimentally tested the automatic non-steam release mechanism by decreasing the heating power as suggested by the previous work. The study reported that the mechanism combined with ceramic insulation reduced thermal loss. Similarly, Podrego insulated the pressure cooker with kapuk wool and conducted a first law energy analysis to find thermal losses. The study showed that insulation reduced energy consumption during cooking. Ogunda Unzi investigated the thermal efficiency of a pressure cooker using kerosene mixed with vegetable oil blends. Based on first and second law analysis, the results showed a thermal efficiency of 52%, which is 20% higher than that of a conventional kerosene wick stove. These studies indicate that heat transfer, phase change, and mass transfer are a key process in a pressure cooker. The present work applies the first law of thermodynamics to a control volume. The cooker's interior wall is treated as a control volume. Heat is supplied from an electric heater and some steam escapes to the vent wall. The system is assumed to be rigid, meaning no boundary work. Energy transfer occurs only through heat input and mass leaving as a vapor. The analysis is based on a few simplifying assumptions. The vessel is rigid, hence no boundary work. There is negligible heat loss to the vessel's wall for simplicity. Heat transfer to the vessel wall is neglected. Vented steam is saturated while exiting the vessel. Negligible bulk and kinetic potential energy compared to enthalpy and internal energy. Initially, the liquid and vapor are at 175 kilopascals and corresponding saturation temperature. Liquid and vapor occupy equal volume initially. At an operating pressure of 175 kilopascals, and 116 degrees Celsius, the cooker receives 500 watts of heat input. Property values such as internal energy and enthalpy are taken from Sengel's book, Thermodynamics and Engineering Approach. Experimentally, pressure, temperature, heat, and mass in the vessel can be measured using a dial gauge, thermocouple, wattmeter, and a weighing scale. The internal energy enthalpy values can be figured out from the property table once we know the pressure, temperature, and the quality. The first law of thermodynamics for a control volume is applied as shown. Since there is no shaft work and negligible kinetic and potential energy changes, the equation simplifies to an energy balance between the heat added, the enthalpy of vented steam, and internal energy. A volume constraint ensures the vessel remains rigid. Now we get the relation between mass and the quality of the mixture. This becomes a linear equation with two variables. The efficiency is useful energy carried away by steam upon heat input. The efficiency is defined this way because the previous studies have shown that most of the heat transfer to the food occurs through condensation. Hence, more steam means more condensation potential. Using the governing equations and volume constraints, expressions were obtained for the mixture quality X2, the mass vented ME, and the efficiency eta. As we can see, these relations allow us to calculate how steam quality and mass vary with time and how much heat contributes to vapor generation. Mass exiting ME is directly proportional to time. One interesting observation is that the efficiency remains constant with time. We can also calculate mass exiting quality and efficiency using other parameters like initial volume, operating pressure, saturation temperature, while keeping other parameters constant, which we will see now. The first plot shows that efficiency remains constant with time at about 0.94, meaning almost all of the supplied energy is used for vaporization. This is constant as the heat venting out due to mass as well as total heat input is proportional to time. The second plot shows that the changing cooker volume has only a small effect on efficiency. The graph is plotted by keeping other parameters fixed, provided in the operating conditions. These plots show efficiency versus temperature and pressure. Even with a plus minus 10% changes in the parameter, the efficiencies varies very slightly. Here we see that the mass loss increases linearly with time as heating continues. More steam is vented. Meanwhile, mixture quality X2 increases slowly, showing that the content remains mostly liquid with a small vapor fraction. To summarize, for a 3-liter pressure cooker at a 175 kilopascal heated at 500 watts for 15 minutes, about 0.2 kg of water is converted to steam. The internal energy per kg of the vessel increases slightly, while the total change in internal energy is negative as the steam escapes through the valve and energy is released. The efficiency is approximately 94% and a plus minus 10% variation in the parameters like time, temperature, pressure causes negligible change to the performance. This study provides the first law estimate of the pressure cooker's performance. However, it is solely based on first law and relies on several simplifying assumptions like neglection of heat to the walls. For more accurate prediction, a second law analysis is required in the future studies. The references include works by Flick, Rocca, Ayuk, Odrago, Ogundaunsi, Sengel, and Vishwanathan. Thank you.